Now that you are familiar with sequences, or sets of numbers that follow a specific pattern, we will now build upon that infinite series. What is the difference between a series and a sequence? We'll discover this in the definition. An infinite series is the sum of the terms of a sequence. Recall that we denote a sequence as a set of numbers with a subscript or an index. An infinite series we might label as counting from 1 to infinity. In expanded form, again, this just looks like a set of numbers. Each element of the set is separated by commas. A series then is built on this sequence, and here's how we denote it. We use the capital Greek letter sigma. When we see that big sigma, it represents a summation. So we're going to sum from k equals 1 to infinity, the sequence represented by a sub k. So notice we have the elements of the sequence listed over here, but because we're summing these elements, this is called a series. So in short, a series is the sum of a sequence. With sigma notation, notice the subscript here is called the index. The value we have at the bottom of the sigma is called the lower limit of summation. So the number up here is called the upper limit of summation. In this case, we're looking at an infinite series, or the sum of an infinite number of terms. Now, it is interesting to note that the sum of an infinite number of terms may be finite. That is, the sum is finite. So you're adding up an infinite number of numbers, yet you achieve a finite sum. While at first this appears to be mind-boggling, let me remind you that you do this every single time you calculate a definite integral. If for a minute we go back to Calculus 1 and we reminisce about those Riemann rectangles, we recall that a definite integral represents the area between the curve and the x-axis from some lower limit of integration to some upper limit of integration. One way that we begin learning how to calculate this area is by using Riemann rectangles. That is, we partition the closed interval from a to b into a finite subset of numbers, and we look at those subintervals and we calculate the area of the rectangle that spans that particular subinterval. And then we sum the areas of those rectangles to approximate the area of the actual region between the curve and the x-axis. So from Calculus 1, you learned that a definite integral is the limit of a Riemann sum. As a reminder, we have the height of each individual rectangle times the width of each rectangle, represented here as delta x sub n, and then we sum the areas of those rectangles to approximate that area. If we let this finite sum tend to an infinite sum, we're actually dealing with a series. This is denoted as a definite integral from a to b. You have calculated many definite integrals at this point in your math career, and you know that they often yield finite values. Integrals can yield finite values. So an integral is an example of the sum of an infinite number of terms still yielding a finite value. And as we'll learn as we progress in our studies, that the sum of an infinite series is related to, but often smaller than, a definite integral. In this section, we're going to learn several techniques for actually evaluating the sum of the series. For most of this chapter, our focus will be to determine if specific types of series converge to a finite sum or diverge to infinity. So let's talk about how we sum an infinite series. we build a sum on what's called partial sums. Definition: the nth partial sum, denoted S sub n, of a series is the sum of the first n terms. That is, S sub n, our nth partial sum, is equal to the sum from k equals 1 to n of a sub k. Remember, this represents the nth term formula, or the generator for each term of the sequence. Our lower limit of summation is k equals 1. Our upper limit of summation here is n. That is, we're going to sum the first n terms to find the nth partial sum. So this is a finite sum. This is evaluated as a sub 1 plus a sub 2, and I continue my summation until I get to that last term as indicated on this upper limit of summation. So the nth partial sum is a finite sum of the first n terms. So let's practice finding some partial sums. Example 1. Find the first 4 terms of the sequence of partial sums for the series sum equals k equals 1 to infinity of 2 over 2k minus 1 times 2k plus 1. Also determine the explicit formula, or nth term formula, for the sequence of partial sum. So our first goal here is to find the first 4 partial sums. So the first partial sum we will denote as S sub 1. That is, we're simply going to generate the first term of this sequence. So we're going to use this formula starting with the index value k equals 1. If we plug in k equals 1, we have a 2 in the numerator. In the denominator, we have first factor here, 2 times 1 minus 1. That's going to give me a value of 1. And 2 times 1 plus 1. That gives me a value of 3. Or we end up with 2/3. So we'd say the first partial sum is 2/3. Let's find the second partial sum. Now, the second partial sum is the sum of the first 2 terms of the sequence. We've already discovered the first term is 2/3, so we need to find the second term of the sequence. We can generate the second term of the sequence by plugging in k equals 2 in our formula. We're going to end up, of course, with a 2 in the numerator. 2 times 2 minus 1 is 3, and 2 times 2 plus 1 is 5. So here we have 2/3 plus 2/15, which will give us, let's see here, looks like 12/15, and this reduces by a factor of 3 to 4/5. So while our first partial sum is 2/3, our second partial sum here is 4/5. Again, that's just the sum of the first 2 terms of the sequence. Let's look at the third partial sum, which we'll denote as S sub 3. This means I'm going to add the first 3 terms of the sequence. Now, don't forget, we've already added the first 2. That's what we discovered as the second partial sum. So we're going to add what we have to this point plus the third term of the sequence, which we're going to generate from our formula using k equals 3. Plugging 3 into our formula, we have 2 in the numerator. 2 times 3 minus 1 is 5, and 2 times 3 plus 1 is 7. So we need to evaluate 4/5 plus 2 over 35. Now, you can either type that into your calculator or just work it out by hand with me. We're going to get 30 over 35, which reduces to 6/7. So our third partial sum is 6/7. Once again, that just means the sum of the first 3 terms of the sequence gives us this particular sum. Per request of this particular problem, we need to find the first 4 partial sums. The fourth partial sum is the sum of the first 4 terms of this sequence. Now, we've already found the sum of the first 3 terms, so a lot of our work is already done. The third partial sum, recall, was 6/7. Now we need to add this to the fourth term of the sequence. That is, we're now going to use this formula to generate the fourth term of the sequence. Plugging in k equals 4, we have 2 times 4 minus 1, that's 7. 2 times 4 plus 1, that gives us 9. Let's go ahead and evaluate our sum. If you have a calculator handy, of course, you don't have to show all this work. Looks like we get 56 over 63. If I reduce that by a factor of 7, our fourth partial sum is 8/9. So what we're doing is generating a sequence of partial sums. Our sequence of partial sums has the first term of the sequence, 2/3, the second term of the sequence, 4/5, the third term, 6/7, and the fourth term, 8/9. Now, what we want to do is see if a pattern is being generated by this sequence. A sequence, remember, is a set of numbers that follows a specific pattern. So, can we determine an explicit formula for the nth partial sum? That is, I want to write a function of n which yields the value of the term of the sequence in terms of its position, and of course position is indicated by the subscript. We can view this particular sequence as separating the numerator and the denominator. Notice the connection between the position of the sequence and the number in the numerator. So when the position is 1 or first in the sequence, the numerator is 2. The second term of the sequence, the numerator is 4. The third term, the numerator is 6. Notice we're doubling the position to obtain the numerator. So if we're talking about the nth or general position, we can simply double that to calculate the numerator. Let's do a similar thing with the denominator. So I want to look at the value of the denominator as a function of the position. So the first position has a denominator of 3. Position 2 has a denominator of 5. Position 3 has a denominator of 7. Position 4 has a denominator of 9. Notice it's very close to doubling the base. If we double that position and add 1, notice the denominator is just 1 more than each numerator. We could say the denominator then is twice the position plus 1. So this is what we call the explicit or nth term formula for the nth partial sum. Now that I have this very efficient explicit formula, I could, if I wanted to, find S sub 100 with a lot less work than we did over here. We would simply plug in 100 into our explicit formula and we would quickly evaluate the sum of the first 100 terms of the sequence. This skill that we've practiced on example 1 is going to turn out to be very necessary for actually calculating not a partial sum, but the sum of the entire series. In order to evaluate the series, we'll apply this theorem. If the sequence, now watch our words carefully here, a sequence is a set of numbers that follows a pattern. If the sequence of partial sums, S sub n, has limit L, then the infinite series, remember the series is the sum of the sequence, the infinite series converges to that limit. That is the value of the series. So what I'm doing here, I'm adding up all of the terms of a sequence, generating an infinite series. I'm finding the sum of those terms. The sum of this infinite series is equal to the limit as n goes to infinity of, notice what I have here. This is an nth partial sum. So if I find the limit as n goes to infinity of the sequence of partial sums, which is also denoted in simpler form here, then the limit of the sequence of partial sums is the same as the value of that series. Let me repeat that again because this is an important concept to understand. The sum of a series is the limit of the sequence of partial sums. It's not the limit of the sequence represented here, it's the limit of the sequence of partial sums. So back on example 1, we began generating a new sequence based on the pattern that's generated by this formula. We generated a sequence of partial sums. We found the first 4 terms of a sequence. From that, we induced the explicit formula. Now, if I can find the infinite limit of this sequence of partial sums, I will have evaluated the sum of this series. So on example 2, we want to find the value of this infinite series, the sum from k equals 1 to infinity of 2 over 2k minus 1 times 2k plus 1. So we're going to apply our theorem to recognize that the sum of this infinite series given by this formula is equal to the limit as n goes to infinity of the sequence of partial sums. Now remember, we found the explicit or nth term formula for the sequence of partial sums. We came up with 2n over 2n plus 1. If we apply L'Hopital's rule, we're going to end up with a derivative of 2 on the top, derivative of 2 on the bottom, or the limit as n goes to infinity of 1, and we know the limit of a constant is a constant. Isn't that amazing? We just added an infinite number of terms together following this pattern, and we achieved a finite sum of this nice, neat integer value of 1. Be absolutely clear that we did not find the limit of this part right here. We converted that into a sequence of partial sums. We generated a new formula, the explicit formula for those partial sums, and found the limit of this new explicit formula for the sequence of partial sums. That limit is the sum of the series. So bottom line, what do you need to know? The sum of an infinite series is equal to the limit of the sequence of partial sums.